This week we're going to be talking about exploratory analysis, and we're going to start off with graphing. So why do we use graphs in data analysis? There's actually a bunch of different reasons that you might use graphs for communicating information about data. You might want to understand the data properties, and it might be too hard to actually look at the whole data matrix of numbers itself. You might want to be able to discover new patterns or associations between variables that might have been surprising had you not been able to look at the data. It can also be used to suggest modeling strategies. We'll be talking about statistical modeling starting next week, and one thing that's very useful is to use graphs to try to inform what kind of modeling strategies that you'll use. Then to debug analyses, we'll also be talking about how you can use graphs and plots to determine where your statistical modeling might have gone wrong. And finally, to communicate results to other people. So exploratory data analysis and exploratory graphs start by focusing on these first 4 steps and not on communicating results to other people. So we're going to first talk about the types of graphs that you might use just to communicate to yourself, to try to understand a data set, not to try to pretty them up and to show them to other people. Before we actually dive into these specific types of graphs, I thought I'd tell you a little bit about the characteristics of exploratory graphs. They're made quickly. The goal is to actually explore the data as fast as you can without having to spend time prettying up the graphs and making them perfect. You can think of it as a rough draft graph for your later final analysis. A large number of the graphs are made, so most of these will get discarded before you actually perform your final analysis, but you have to make a large number of them to explore all the potential avenues that the data might take you in. And then the goal is for personal understanding, not necessarily for communicating to other people. So if you don't need color or different sized points to be able to communicate to yourself, you don't necessarily have to do that in your exploratory graph. Color and size are primarily used for information communication to yourself rather than to make things aesthetically pleasing so that they'll be easy on the eye when people look at your data analysis. I'm going to start off with a little bit of background before we dive into very specific types of graphs. And so I'm going to talk about a little bit of theory and experimentation that has been done in the graphical display of data. So the first thing that I thought I'd talk about is the ways that you can display a comparison between 2 quantitative measurements. So here are 9 different ways that you could actually display them. So for example, you could, if you had 2 measurements, you could say they were 8 and 4. You could put them on a common scale like this, and then it's relatively easy to be able to tell which one is bigger than the other. You could also plot them but on different scales or on scales that aren't aligned to each other. You could make 2 different lines of different lengths and compare them. Or you could create, say, 2 different angles that were proportional to the 2 data points, or 2 circles of different areas. You could also do things more complicated like volume of shapes, curvature, or shading. Depending on the type of task that you're doing for your analysis, some of these ways of encoding information might be easier or harder for people to understand. And in fact, people have done experiments to try to determine what are the easiest ways to communicate information and what are the most effective ways to communicate information in graphical displays. So I'm going to tell you about a couple of those experiments and then summarize some of the key ideas you should think about when creating your graphs. So first of all, if you're going to be making comparisons between quantitative measurements, here's an experiment that tells you a little bit about how those measurements and how those quantitative displays should be arranged. So these are 5 types of graphs, and they were shown to 55 people in this experiment in the paper that I've linked to here. And they were asked to compare the measurements for each of the 2 dots in each plot. So compare the value for this bar to this bar, then compare the value of the length of this bar to the length of this bar. The same thing here, these 2 dots represent the 2 values being compared. These 2 dots represent the 2 values being compared, this box versus that box, and so forth. So in each case, the goal is to try to compare which value is larger, and in some cases, the values are easier to distinguish than in others. So we're going to be talking about this in just a minute, but if the 2 values are right next to each other and encoded as lengths, they're very easy to distinguish. On the other hand, if the 2 values are encoded on different scales and not right next to each other, they might be harder to distinguish. So here are the results of the analysis that they performed when they did the experiment. So what you see here are the different types of graphs, so type 1 through type 5, and in each case the goal was again to compare the values that were indicated by the dots. On the x-axis is actually the value of the error that they achieved, and the dot is the actual mean error, and then the two bars are the confidence intervals for that error. We'll be talking about confidence intervals a lot next week. But what you can see is that the one with the smallest amount of error was when the two bars were displayed right next to each other and they were compared on a common scale. And it got more difficult as the tasks moved from left to right. So it actually shows you a little bit about what are the kinds of ways that you should display data in order to most accurately communicate the differences that you're trying to identify between measurements in a quantitative fashion. Another experiment that they performed, and this is the experiment that caused, I think, a lot of people to not like pie charts. So you'll often hear that statisticians don't like to use pie charts, or they'll rail against pie charts in their discussions. And the reason was largely because of this experiment. So in this experiment, there were 5 different data points, and they were quantified either as an angle. So the goal here is to compare the angle of B to the angle of A to see which one is larger, versus just comparing the lengths, A versus B versus C, and so forth. And so again, they performed a similar experiment where they showed these graphs to people and they asked them to make different comparisons. And then they showed the error rate for the 2 different kinds of comparisons. And so in the case of position, using position or one of those bar charts, the error rate was very low, whereas when you were using an angle, the error rate was much higher. And so that's because there's actually psychological and neurological reasons why it's easier for people to make comparisons on lengths rather than areas or angles. They actually did further experiments. I'm not going to talk too deeply about this, but you can take a look at this paper if you want to learn a lot more. And they basically showed that using positions on common axes or non-aligned axes are still much better than using measurements of length, angle, slope, or the area of circles, or the area of blobs. And so basically what this is suggesting is that when possible, when you're trying to perform graphical displays of data, you should try to use position as opposed to length, and then definitely not the circle area or blob area or angle of the graphs as a way of comparing quantitative information. So just to summarize some ideas, this is of course a really brief summary of what is an incredibly large area of research into the graphical display of data. And the summary would be: use common scales when possible. So try to make your plots so that if you're comparing lengths or if you're comparing positions, they should be on a common scale. And when possible, use position comparisons. Again, as I've said before, pie charts aren't necessarily the statistician's best friend because angle comparisons are frequently hard to interpret, so they should only be used sparingly. We didn't discuss too much about this in the experimental results I just showed you, but 3D bar charts and comparisons of volume are actually much harder to perform than some of the other tasks, and so should also be avoided whenever possible. So I'm going to give you a couple of examples of the different kinds of plots that you might make and what they might be useful for. And I'm going to use this American Community Survey data that we've actually used in a previous quiz for making these plots and for showing you the different kinds of comparisons that we can do. So first I'm going to just read the data into R using this command here. Alternatively, if you had the ss06 pid.csv somewhere else, you would have to change the path to be able to load the file in. So the first type of plot that we're going to be talking about is called a box plot. And so a box plot is a type of plot that you would use for a quantitative variable, and its goal is to try to give you an idea about what the distribution of the data looks like. So what you see here is the command that you would use to create this plot. You would type boxplot and then pass it a quantitative variable. I've also changed the color to be blue so that the plot is a little bit easier to see, but this isn't necessary to make the plot. So what you see here is the box plot of the ages for this study that we're looking at. And so what you can see is that there are several different values that are encoded in this box plot. The thick line in the middle of the box plot is the median. So that is a measure of the center of the distribution. And in this case, it's just under 40. You also see the 75th percentile and the 25th percentile of the data as the upper and lower bounds of the box. And then what you see are some whiskers. These are called whiskers. And then up at the top, it's the value that's 1.5 times the 75th percentile. And here it's the 25th percentile, 1.5 times lower. And so if there were actually values that were either larger or smaller than that, you would actually see those values sort of as dots represented above and below the whiskers. So what is this plot good for? It gives you an idea of the distribution of the data. You can see, first of all, if the data have really large number of values spread out, or you can see if it's very compact distribution. You also can see that if the distribution is symmetric or not by where this black line falls in the box. If the black line is sort of close to the center of the box, the distribution is a little bit more symmetric. Whereas if you see the black line sort of pulled towards either the top or the bottom of the box, you actually see that the distribution would be a little bit asymmetric in that you would see more of the values being low or more of the values being high. So this gives you some information about the quantitative distribution of a single variable. And so you can actually use box plots to make comparisons. Again, the goal is to make them on the common scale, so you can actually use the box plot command to make comparisons of quantitative variables on a common scale. In this case, what I've done is, again, I've used the box plot command, but now I take this quantitative variable and I apply a formula. We'll be talking a lot more about formulas when we talk about statistical modeling in R, but basically what I do is I say, I include this little tilde which says, show me the distribution of age broken down by the difficulty dressing variable. And so the difficulty dressing variable has two different values, and so I've created a factor here, one level of the factor for each level of the difficulty dressing. So DDRS equal to 1 means that they have difficulty dressing, and DDRS equals 2 means they don't have difficulty dressing. And so what you can see here is that the individuals that have difficulty dressing actually have a much higher age on average than the individuals that don't have difficulty dressing, which is sort of not surprising. But by putting these on sort of a common scale, it makes it possible for you to compare sort of the centers of the distribution, but also the variability of these two distributions. Now, something that isn't encoded in this plot so far is any indication as to how many individuals we have that come from that have difficulty dressing versus how many individuals we have that don't have difficulty dressing. And so we can actually encode that information with a variable or with a parameter called var_width. So again, this is the same box plot of age, and we use the tilde to say I would like it broken down by whether you have difficulty dressing or not. Then I've also passed it two colors, blue and orange, and these colors correspond to the two different groups of the difficulty dressing factor. And I've also passed it names, yes and no, so that I can actually see which individuals do have difficulty dressing and which don't. And then I pass it this parameter var_width equals true. So by passing it var_width equals true, the width of the box is proportional to the number of observations that we have in that group. So you can see here, for example, that the group that has difficulty dressing, we have a much smaller number of those individuals than we do in the group that doesn't have difficulty dressing. So ideally, if you're making comparisons like this, you'd like to see about an equal number of observations in the two groups. You'd like the two boxes to be about the same width. And this gives you some idea, if this is much, much smaller than that, the difference in, say, centers between the two distributions might not be quite as meaningful, because this might not be very many data points at all that are contributing to this estimate of the center here. So another type of plot that you can make is called a bar plot. So we saw an example of those bar plots earlier when we were discussing the different kinds of plots and how comparisons on length are maybe not as useful as comparisons on position. So this is an example where you would make a comparison on position. In this case, what I've done is I've made a table of the different values here of this variable CIT in the data set, and what I've been able to do here is then make a count of each level of this variable CIT as 5 levels. And so I made a bar plot of those levels, and what it does is it now makes a bar that's height of the bar is equal to the data value that you're seeing. So the first level of CIT has about 14,000 values, and the second level has much smaller number of values, and then it's sort of increasing up to 5. So what this allows you to do at a glance is to see sort of the number of observations that you have in any particular class, and it's very useful for breaking down sort of tables of qualitative variables, but can also be used to compare the sort of the means of quantitative variables and so forth using the bar plot command. Next are histograms. So histograms are sort of like box plots in that the goal is to quantify or sort of look at a univariate distribution of data or a single variable distribution of data. And so what I've done here is I've made a histogram with the hist command. Again, I've passed it the age variable and I've colored it blue to make it easier to see. So this is what a histogram looks like. So what a histogram is a little bit different than a bar plot. What it does is it says, okay, I'm going to look at how many values in the data set of age do I see between 0 and, say, this looks like about 4. So in the data set, I see about 1,200 values, a little over 1,200 values that are between 0 and 4. Then it goes and it looks between 4 and 8 and so forth, and it looks and sees how many values are there, and you can see sort of that there's not quite 1,200 values between 4 and 8. And it goes on and on like this. And so, for example, way out here, you see that between, say, 88 and 90, there actually aren't very many values at all, and so this bar is much, much lower. So the nice thing here is it gives you a little bit of information about the distribution and maybe a little bit more information than the box plot, in the sense that you can actually see the shape of the distribution here. So you can see that there's sort of a relatively large amount of small ages, and there's also a relatively large amount sort of in middle age, but sort of in this place in between there are fewer values, and also sort of out at the tail there are fewer values, which is a little bit more information than you got from the box plot. So another thing that you can do with histograms is you can actually set the number of breaks. So this is the number of breakpoints there are. You can tell it, instead of breaking it down between 0 and 4, you can say, I would like there to be a lot more bars. So for example, this bar might be now just the values between, say, 0 and 1, and so you can see that there's quite a large number of those values in the data set. And you can actually sort of see the full distribution broken down much more fine-grained by setting the breaks to be larger as a parameter in this data set. I've also, in this case, changed the title of the plot using the main parameter to age, which makes it a little bit easier to communicate what's going on here. So again, this is on the frequency scale, and you're able to see the frequency of the observations of a particular size. Another way that you can do this is you can actually create what's called a density plot. So a density plot is like a histogram, but it's been smoothed out. So to do that, I actually first use this density command, and so I pass it the quantitative variable age to the density command, and then I make a plot of that object that gets created with the density command, and I tell it, in this case, how thick I want the line to be. This is LWD, is how thick you want the line to be. So by setting it's by default equal to 1, by setting it equal to 3, I get a slightly thicker line here. And again, I make the color blue so it's a little bit easier to see. Again, what you see here is the age distribution. And so now you see density, which is a little bit different than frequency. So the difference between density and the frequency that you saw on the previous histogram is the shape is sort of similar as you saw in the histogram, but what's going on here is, instead of calculating the exact number that appear between 0 and 1, it's looking at something like the percentage of the observations that we see that are between 0 and 1. So something like a little under 1% are this value here, and whereas for sort of people that are above 80, the percent is even much smaller. The other thing to note here is that because it's been smoothed, you see that this shows the same sort of shape that the histogram showed, but you now, by smoothing, have also induced a little bit of error at the boundaries. And so, for example, we actually haven't observed anybody with age smaller than 0 or age greater than 100, but the smoother actually kind of extends a little bit farther out, so you have to be a little careful about interpreting near the boundaries. The reason why you would want to use density instead of, say, a histogram is that you can actually overlay the distributions for different, say, genders of the age variable. So what I've done here is I first created a density based on all of the age measurements that we have for all of the individuals in this study. And then I also subset that data set to only the individuals whose sex variable is equal to 1. Those are all the males. And so now I actually make a density of the ages of just the males in the study. And so what I can do is I can again plot the density function that I calculated for the age variable, and so that appears in blue. And so you can see that that distribution looks like this. You can see the blue line there. And then I can use something that's called lines to add another line to this plot. And so when I use lines, I pass it the other density, the one I calculated for males, and I color that one in orange. And so you can see actually the distribution for males is very, very similar to the overall distribution, but there are some slight differences in the frequency of ages for males versus the ages for everyone overall. And so the nice thing about this is that you can compare multiple distributions. Even though there might be some slight sort of error in terms of display of information, it makes it easy to compare multiple distributions, whereas with histograms that's not as easy. So those are some very basic univariate plots that we'll be talking about, and in the next lecture we'll cover some more complicated plots.